Honorable Chairman of the session, Professor, Researcher, students, and the audience. Good evening from South Korea. I am going to discuss the computational analysis of nucleophilic substitution reaction of phenyl carbonyl isothiocyanate with pyridine in the gas and solvent model. This substitution reaction usually run through two different paths where one is stepwise, one is conservative. Both of the paths constructed by or associated with associative type, both of the paths, or dissociative type, or backside nucleophilic attack, or frontside nucleophilic attack, and finally transnative product. Our system is phenyl carbonyl isothiocyanate. This one is substrate, and nucleophile is pyridine. So X is the nucleophilic substituents, and Y are the substrate substituents. Relevant substituents are here. DFT calculation was done by using D3-LYP functionals, and 6311 GDP basis set was considered. We also considered the dispersion, empirical dispersion correction using GD3DJ code. Validation of this reaction was confirmed by frequency calculation, IRC verification, thermodynamic parameters, and free energy of gas and solvent polarization model. The central atom, that carbon reaction center of the phenyl carbonyl isothiocyanate, and the nucleophile is the pyridine. This is the pyridine nucleophilic nitrogen, and the living group is this one, NCS living group, isothiocyanate living group, nitrogen, this one, and phenyl oxygen and carbonyl oxygen. So these four atoms, nucleophilic nitrogen, carbonyl oxygen, living group nitrogen, and phenylic oxygen as ligand was considered for these all structural features. Taylor function was considered in this case for first order using the kinetic, and in this case we calculate the reaction constant for rho X using the nucleophilic substituents, Hammett substituents, and rho Y for the substrate Y substituents, Hammett substituents of Y values, Y, and also we use pK value for nucleophile, and in this case we find out the beta X value. Finally, we calculate the rho X value using this equation for this whole system. So we can go directly to the result and analysis. So this is the bond perturbation. We use the non-substituted nucleophile and substrate, and substituted substrate and nucleophile, and their TS structure in the structures in the TS state. So we consider and we find out the variation between the bond length of carbon nucleophile nucleophilic nitrogen bond length, carbon phenylic oxygen bond length, carbon carbonyl oxygen bond length, and carbon and living group nitrogen bond length. So all that bonding difference in the TS we treat against the substituent Hammett substituent constant and find out the linear correlation. From this value, we can find out how that TS are associative type, more tighter TS it can form. From this result, we can find out this one. Y substituent variation when we plot, and from this result, we can find out that Y substituent play the role to the departure of living group that can assist. And here in the solvent model, we can find out all the bond variation, and from here also we can find out the tighter TS. But interesting is in this case the role of this reaction of bond breaking in this case, the solvent polarization and the Y substituent playing the major roles that can be find out from this table and the display of the correlation, linear correlation. This is the Pauling bond valence bond length coefficient, and from this bond valence bond length coefficient usually express the bond softness, and from this bond softness we can find out that there are two hydrogen bonded cyclic structure in the TS. That can be the reason for tighter TS in this case. In the solvent model, equally we can find out from here in the gas phase how living group is living out with the assistance of the Y substituent effect, and in the solvent model the polarization effect and Y substituent can play a role to the living group departure. In this case, this is the NVO charge calculation and others, bond coefficient, dipole moment, etc. So we consider similar substituents in the nucleophile and substrate to find out the effect of the substituents. Here, major things is in the solvent model, gas phase, we can find out the dipole moment is very low compared to the solvent model. That can express or indicate that the solvent polarization play one fundamental role for this reaction. This is the intermediate structure. This is one deuterionic structure. We already know that neutral nucleophile and neutral substrate when react, then it form the intermediate, it should be ionic. So in this case, we find one deuterionic intermediate, and its orbital structure can be shown in this way, arbitrary structure. We also calculate the energy profile for this reaction. Mainly, I want to show in this state that this is the free energy of the reaction, and this is the activation energy for the reaction. In the bracket, all that energy for the solvent model. And if you see, then you can find that in the solvent model, the activation energy is much lower than the gas phase. So we can expect in the gas phase, it produce one endergonic reaction, and in the solvent model, it will be exergonic reaction. And also, we can find that the energy activation barrier is much lower in the solvent phase than in the gas phase. We also calculate the Hammett and Bronsted coefficient, and we calculate as indicated or as discussed earlier that by using the Taylor function. So here we calculated the reaction constant rho x based on the Y substituent variation, and rho y based on X substituent variation in the nucleophile. And also we calculate the beta X value with the variation of the nucleophilic pK value. And so we find out the result. We can speculate from this result. Here, positive beta X value and negative rho x, large negative rho x value we can see. So also we can see that here the cross interaction constant, which one is calculated, this one is positive. So from here, positive nucleophilic positive value for beta X and the negative value of rho X. So negative rho X usually indicate the much charge transfer, huge charge transfer from nucleophile to the electrophile or reaction center. So nucleophile become positively charged, and it generally create the azonium type charge center. And also beta X value that indicate that with the more negative nucleophilic interaction, rate of the reaction become much higher. That one it can indicate. This is the correlation, linear correlation that nucleophilic substitution that rate constant we calculated, and this is the Hammett substituent constant of nucleophile. If we plot, then we can find in both cases, we can solvent phase and gas phase, we can find linear correlation, except some of the deviation from the electron accepting nucleophile. And here, this is the linear correlation for the pK value of the nucleophiles in the gas phase and also in the solvent phase. Bronsted coefficient in the solvent model, when we calculate, then we can find the reaction constant for rho X for the Y substituent variation, rho Y for the X substituent variation, and beta X for the X substituent variation. pK value of the nucleophile. And then we can find the beta X are negative and rho X are large positive. So large positive, large negative beta X value usually and positive beta X, rho X value, it usually indicate the generation of negative charge in the nucleophile in the TS that it can indicate. And also here another important thing is that negative beta X okay, so it can produce, and also we can find out the cross interaction constant. That one is positive 0.87. So this positive cross interaction constant usually indicate the stepwise mechanism for substitution reaction. Here we calculate the reaction profile for IRC path. From this IRC path, it is clearly indicate for different state of the structure on the IRC path. For example, that reaction complex, intermediate, TS, product complex, etc. for gas phase, and blue one for the solvent phase. And also you can see here that energy barrier is much lower in the solvent phase and higher in the gas phase. And in the gas phase, it is inorganic reaction, and in the solvent phase, this is exergonic reaction. We also calculate the force constant for different steps of the structure and their work function. So work functions are divided into 6 parts in the whole coordinate, reaction coordinate from W1 to W6. W1 and W6 are mainly rearrangement for structural rearrangement, and W2 to W5, these steps usually charge reorganization. So that we can find out from here. From this calculation, we find out the work function of all steps, and from there we can find out the activation energy reaction energy, intrinsic activation energy, and the Bronsted coefficient as beta. So here, Bronsted coefficient usually related to the Hammond postulate, and which one indicate that this TS is early or later. If the Bronsted coefficient value is larger than half, then it indicates the later TS, and if smaller than half, it indicates the early TS. So we can, what we speculate, what we find out from the previous data, previous analysis, this data support that one. And here, this one is reaction force profile. So in the force profile, if that force constant is gradually lower, it indicates the gradually higher, it indicates the spontaneous process, means the bond making. And if gradually lower, then that indicate the bond breaking process in the system. So in the gas phase and in the solvent phase, we analyze and find out both of them. Here, reaction electronic flux, and this flux actually indicate the electronic transformation, that electronic activity during the change in structure, or during the course of the reaction in the reaction coordinate, IRC path, how charge is distributed and reorganize the structures. Here, this is Y-bar bond index throughout the IRC, intrinsic reaction path. And from this profile, we can see that in the gas phase, it is later TS, it indicates the later TS, and in the solvent phase, it is much early TS. From the calculation, we also calculate the energy profile for different structure steps with their energy, and we can generate this reaction path for the reaction course of reaction by using the dual descriptor densities. And here we can show the dual descriptor densities for different steps like RC, reaction coordinate, then Xi1 for the next step, then intermediate step, and in the Xi2 in this slide and next slide, this is tension state structure, Xi3, and this is the product complex. So here, blue orbitals indicate the negative charge lobes, and the green lobes indicate the positive charge area. So finally, we can calculate the 3D feature of the energy hill. You can see here, and also we generate the energy contour map, and from here we can find out how that reaction move from the reaction complex to the product complex throughout the intermediate and TS. And it follow this profile also indicate the two-step reactions in this case. So stepwise nucleophilic substitution can be proved by using all sorts of information and data. Thank you very much. And if you have any question, please email me.